All right, we're back. We're going to be in Note 17. We're going to be on page 8. We're going to start talking about polar areas, but I think the easiest way to start that is to watch them traced out because they're not traced out the way your brain maybe initially tells you that they're going to be traced out. So what I've done is I created a thing on GeoGebra. Honestly, I don't know if I even remember how I created it. It has like one flaw, but the flaw is actually, is it a feature? I don't really know. So I'm going to graph 1 minus sine of x. And while I graph it, I'm also going to shade in the region that has currently been graphed. All right, so let's watch how this happens. So I'm actually just going to like step through it a little bit. So you can see, because of the way you plot in polar, it's like you start at the origin, you plug theta in, and then you just move out that value. You're always graphing sort of these wedges, right? Like pizza slices. They're really sectors. So you can see this is how it's plotted, and then this is way too slow. So I'm going to start dragging. So if I drag it, now this is when r is equal to 0, we're here. Then we're just going to keep going. Past pi over 2, we'll go toward pi. You can see, like if I stopped right here and I integrated something, right? Like we know that integrals give us areas. If I integrated something from 0 to 2.86, it would only give me this weird region, like all the shaded stuff. If I keep going till I get to like pi, it would give me this, right? So, or I could have just gone from 0 to pi over 2 and doubled it, and it would have given me all of this area. If I keep going, I'm going to go until I get to like 3 pi over 2, which I don't exactly know the decimal for, but it's got to be right around there. So 3 pi over 2, I'm getting just this part of it. Pretty weird. So you have to get used to this fact to like really understand how polar areas are being traced out. The way that I think of them is like you have the curve, right? Like imagine the curve already exists. You've graphed it. Now you're going to stand at the origin with like a laser pointer, and you're just going to rotate. And as you rotate, the laser pointer sweeps out the area that has already been graphed or been defined. So if we started facing the positive x-axis and we rotated 3 pi over 2, our laser pointer would have hit all of this region. And so if we integrate something from 0 to 3 pi over 2, we'll get that area. If we integrated from pi over 2, which was like right here, the first time we hit the origin, if we went from pi over 2 to 3 pi over 2, we would get half of the area, and then we could double that to get the full area. When you're doing polar areas, you frequently find part of it and then double it. And you can see here, if I went all the way from 0 to 2 pi, I would definitely get the full thing. So it's these types of regions. Like if I stop there, I get that weird sectory type thing. That's what's a little bit different about polar. So you're not making rectangles. You're not making rectangles that are like vertically aligned. What you're actually making are little sectors, like pizza slices, that are coming out of the origin, and then the edge, kind of like the crust of the pizza, is along the polar curve. Let me change this up to something that has an inner loop, just so you can see one of the potential pitfalls of what can happen. So I'm gonna do this. So this, let me just go, we're gonna go step by step, right? So 0, if you set r equal to 0, you get sine of theta equals 1/2, so pi over 6. By the time I get to pi over 6, I'm here. Now I'm gonna start the inner loop. So from pi over 6 to pi over 2, you can see we're tracing out this, which is great. We get this. All right, so that was from 0 to pi over 6 gave me this first wedge. From pi over 6 to pi over 2 gives me the second kind of wedge thing. So if I went from pi over 6 to pi over 2 and then doubled it, it would give me the entire area of the inner loop. So I'm going to go to 5 pi over 6 is the next time sine equals, is the next time, 5 pi over 6 is the next time sine equals positive 1/2, which means if I plug 5 pi over 6 in there, I'll get 0 for r. So there we go. So from pi over 6 to 5 pi over 6, we get this inner loop. Now by the time I get to pi, I'll be out here again. And then I'm okay until I get to 7 pi over 6. 7 pi over 6, something weird is going to start happening. At 7 pi over 6, we already traced out this area. So watch what's going to happen. This is like a weird artifact of the way that I designed this. it's going to unshade the area because it's already shaded and it doesn't want to double count it, so it just uncounts it, whatever that means. This shouldn't be happening. What should be happening is you should be getting a darker purple color because you're actually tracing over it twice. So that region there that appears to be not filled in is actually filled in twice because we counted it once when we went from pi over 6 to pi over 2. Now we're counting it again when we go from 7 pi over 6 to 3 pi over 2. So we actually have double counted this. Double counting is the annoying part about polar areas. We have to be really thoughtful about, have we already counted a region, and if we have, how can we avoid double counting it? And then if I keep going, I'm going to keep double counting that region, which is why it isn't filled in, which I don't remember why that's happening, or if I even ever knew. And when we get here, we're good. So how could I have gotten the whole thing? Well, what if I just went from, so this is pi over 6 is the first time I hit. Pi over 2, okay. 5 pi over 6. What if I start at 5 pi over 6? Just start at 5 pi over 6. Keep going. So since I'm starting at 5 pi over 6, I never did anything that's currently filled in. Then I'm going to keep going 5 pi over 6 to 3 pi over 2. So if I just went from pi over 6, maybe I can type it in. I don't know what's going to happen here. If I go from 5 pi over 6 to 3 pi over 2. Yeah, that does nothing. Oh, you know why that does nothing? It does nothing because of the way I define the curve. I don't want to work that out, so I'm not doing it. But if I had just gone from 5 pi over 6 to 3 pi over 2, so what did I do here? Plus like 0.1, 0.01 or something. If I just go from 5 pi over 6 to 3 pi over 2, that gives me all of the area counted only once, or half of the area counted only once. Double it, and you get the full thing. This is the idea. So now what I'm going to do, I'm going to switch to the notes. It's going to be a blank page because I need to write some stuff out. And then in the next video, we'll actually like get down to doing some areas because this one's probably already kind of long. All right, let's figure out how we can find polar areas. So polar areas, first, let's just start with like a picture. It doesn't need to be good like this, right? And what we're going to do is we are going to have a radial line where we'll start finding the area, and then another radial line where we're going to stop finding the area, right? And I'm going to call this alpha, and I'm going to call this beta. Okay, so those are radial lines. They're theta equals alpha, theta equals beta. Now what we do is within this region, we're going to create some sectors. So like I'll go to here, do it, become a line. You know you want to. Go to here, and I'm just gonna like make a sector, slice pizza. And I'm using that like the more rotated radius is gonna be the radius of the sector. I'm gonna do it again. And I'll make another one. And then I'll do it again. So you can kind of feel like we're building like a Riemann sum type of thing, because we are. Dang it. So I think that if I like go past, let it become a line, and then go back. That's like the best. And then here we would do this. So what I really want to do is add up all these sectors. And then I want to make more sectors and more sectors. And I want to really use an infinite number of sectors. So each of these well, let's talk about the area of a sector, right? So the area of a sector. So the area of a sector is, it's really just a fraction of a circle, right? So it's like theta out of 2 pi times pi r squared. And if we simplify some stuff, like gone, so it's going to be 1/2 r squared theta. That's the area of one sector. So let's say sector, right? So what we're going to do, this is all very Riemann summish. We're going to create a delta theta, which would be beta minus alpha divided by n, the number of sectors that we want to have. We need a radius sub I So our radius sub I, think about it, you start at alpha and you're just going to keep adding delta theta to get each of them. So I'm going to say that that's going to be alpha plus I times delta theta. You're never going to do this calculation, so you don't really need to worry about like all the like fine details, but like, doesn't this feel like a Riemann sum? It feels like we're just writing like rectangles. We kind of are. It's that our rectangles are sectors. Polar rectangles are weird. They're sectors. So what I want to do is like sector sub I would have area 1/2, and then r sub I squared delta theta, because that's the angle that we want. All the delta thetas are going to be the same. They're all beta minus alpha over n. So what I want to do is sum up all the sectors. So the total is going to be approximately from I equals 1 to n 1/2 r sub I squared delta theta. But then if I take the limit as the number of sectors goes to infinity of this summation, this is a true Riemann sum right here. This is going to become, so I can take out the 1/2. The limit of this summation becomes a definite integral, and we're going to start at alpha, end at beta. Then we're going to get r squared d theta. This is it. This is how you find the polar areas. There's a 1/2 and there's an r squared, and it's like mind-boggling. It's not mind-boggling at all, because it's all based on the area of a sector. That's where the 1/2 is coming from. That's where the r squared is coming from. You're just making little pizza slices and you're adding them up. You're making an infinite number and you're trying to add them up. So the formula itself is summarized here. And there is, so the inner loop thing is going to be a big deal. We're going to deal with it. You don't really want, in any particular XY region, you don't want the polar curve to pass through it twice. If the polar curve passes through an XY region twice, so what do I mean by that? Basically, if it passes through an XY region twice, start to worry, right? So I'm going to draw an inner loop sine curve with an inner loop, right? So okay, so if you take a look, this region, that's an XY region where the polar curve passes through twice. So this is going to give us some trouble, some issues, not really trouble. We have to be more mindful of that. If that never happens, if there's no XY region where the polar curve passes through it twice, just go for it. You're just going to be great. So I'm going to come back in the next one, and we're going to start doing these. We're going to do something a little weird. We're going to start with things that you ordinarily probably maybe don't feel like you should use polar for, because we'll have a sense of the answer, and that's really important. So be back in the next video where we will get going on these problems, and I will see you there.